See if we can have one.
Great.
Are you living in Hamlin?
Yes, I am.
Oh. Where are you staying?
So we're renting a house northeast of campus,
Oh, I see.
Park Lake Road.
Yeah. When did you arrive?
So I actually arrived,
Oh, wow. Sit in your office is upstairs?
yeah, I'm next to him.
Across the hall? Are you across the hall?
No, just next to him.
I saw Paul's office open today. Is he back?
Yeah. Where was he?
He's been going over in the fall. The electric amplifier. So he was in electric month.
So I guess it's already a minute past 11. Let's just get things started here. Can online people hear us right now? Oh, the chat. Yeah, okay. Yeah, okay. So today we are having Chuck Horowitz from Indiana University giving a seminar here. In fact, he is actually on sabbatical. He will be here for a year. So anyone interested in talking to him anytime, his office is close to mine. And so first of all, like just give me some basic information about the speaker today. He's an expert in theoretic nuclear physics and astrophysics. And I highlighted a nuclear theory actually, because in his website, he claimed to be a nuclear astrophysicist. I don't know when he decided not to be a nuclear theorist, but he's definitely a nuclear theorist. So he got his PhD at Stanford at 1981, and then become a postdoc fellow at the Niels Bohr Institute and MIT between 1982 and 1983. And then he became a assistant professor at MIT between 84 and 86. After that, he went to Indiana University and first as the associate and then full-time professor there. And he has a very broad research interest, and just pick up a few items out of his website. And for example, gravitational wave measurement signal, based on that, extract the neutron-rich dense matter equation state. And also he is an expert in molecular dynamic simulations, applied it in the neutron star-crossed physics studies. And also he's involved in neutron radius measurements for nucleus in the JLab experiments. And of course, there's many more research topics. Just as a personal interaction with him, I actually got my thesis, PhD thesis at Indiana University. My office was just close by. My thesis was the topic. One key topic was actually suggested by him. Like just one day, my advisor Brian Surratt and me didn't know what to do with my thesis and went to his office. And he suggested, okay, why don't you calculate this neutral current induced photon production of nucleus? And the photon, the energy is in the range of hundreds MeV. Okay, It's not typical low energy nuclear theory, but it was a very important topic, like was brought up in our previous theory seminar by people from Fermilab, right? About the minimal low energy access. Anyway, that's just a personal note. And okay, it's all.
Great. So thanks for the introduction. I hope it's obvious, but please interrupt. The last of my talk I get through the back.
Very well.
So, wanted to start. So neutron skins of nuclei and neutron stars and some astrophysical measurements of the stars and the PREX and CREX measurements of neutron skins in nuclei. So I thought I would start with the standard model of nuclear physics, 1980s. We had phenomenological two-body potentials, the phase shifts. The three nucleon force is assumed to be small. So that was, if you like, the definition of the standard model. Why we assumed three-body forces were small, I think the reasoning was sort of twofold. One, that this standard model sort of worked. So you could calculate a bunch of things in nuclear physics, and it wasn't so bad. And the other reason is we had approximations solving the many-body physics at the time. Our many-body wave functions had approximations. And since we had errors in the wave function, it didn't seem to be worth it, perhaps to include complicated three-body forces if we already had others. Okay. One interesting feature of this model is it's actually more predictive than the present standard. You want to predict the neutron star equation of state in the structure of a neutron star, then in this model you just calculate. There's no chiral scale. We can use the model at any density. Okay. Then they broke the standard model. Early 1980s, some extraordinary, beautiful calculations in hindsight, calculating the energy of nuclear matter. He finds that nuclear matter saturates with the wrong density and binding energy, and in fact, it can saturate at up to twice the correct density. Okay, and there's beautiful calculations, especially for the time. So at this point, there was no way out. You needed three nucleon forces. Okay, so he broke the standard model, and it recovered only partially. So some of the predictive power was never restored. We can't calculate the matter and high density in a neutron star. And what we tried to do next, since we need three nucleon interactions for nuclear saturation, we tried phenomenological three-body potentials, but nobody could agree on them. They're highly arbitrary. So we were lost. And at this point, the organizational scheme provided by chiral effective field theory is completely crucial. So I want to emphasize we need that. Of course, you expand two nucleon, three nucleon, et cetera, interactions and powers of a momentum over.
In this calculation, what are the experimental benchmarks? I mean, you know.
That's actually something I want to get to. So the nuclear saturation is very important. So I want to talk about that in a second. We're interested in neutron stars, And a question a lot of people ask is when, at what density does chiral effective field theory break down? That's a good question. An even better question is how does chiral effective field theory? So if we watch it break down, maybe how it breaks down is going to tell us, provide some insight about the nature of denser matter. Okay, so I think that's a good question to focus. All right. Nuclear saturation is fundamental. It's really important to nuclear physics. And let me say nuclear saturation two ways. Infinite nuclear matter has a minimum binding energy. So the binding energy versus density, that curve has a minimum, about 16 MeV of binding energy, and the folklore is 0.16 nucleons per cubic. Okay. So that's our definition of nuclear matter. And I think the folklore is basically predictions of density functional. So if a density functional fits charge radius and binding energy of a range of nuclei, it tends to saturate there. But that's not an observation. Okay, so that's one way of saying nuclear saturation. Another way is that the interior baryon density of a heavy nucleus is approximately independent of mass number and is approximately constant as a function of R. And this constant is close to where an infinite system would saturate. Okay. So this is a heavy nucleus has a more or less constant density inside, and that's nuclear density. Okay, so this is observational, except our observations are incomplete. Okay, so here are charge densities, and you can look at these for a while, and it's not particularly a complete description of nuclear saturation. And furthermore, we expect a constant baryon density, and here's this number, 0.16 nucleons per cubic Fermi up here. So that's, and of course, we'd like to see the neutrons, since these are just the protons. Okay. Great, and the charge densities, of course, are measured in electron scattering. You measure a cross-section over a large range of momentum transfer. And in this case, Ingo 6 directly inverts this and gets the black dashed line. That's the experimental charge density for lead-208, density versus radius. That little wiggle there is the 3s shell structure. There's about a 1% experimental error at small r, and that's not shown here. So this is a very accurate direct determination of the experimental charge density. And of course, we want to follow this idea, but do the neutrons. And so we're going to use parity violation. The weak charge of a neutron is large, and weak charge of a proton is small. So the weak interactions at low momentum transfer exceed the neutrons. What we actually measure is the parity violating asymmetry, the fractional difference in cross-section between positive felicity and negative felicity electrons. It's the interference in Born approximation of a weak amplitude order G Fermi, momentum transfer squared, and then a weak form factor. This F weak is the Fourier transform of a weak charge density, and this weak charge density is mostly the neutron density. So we have an electroweak reaction, It's free from most strong interaction uncertainties. It's a clean but difficult way to, in principle, map out the distribution of weak charges and neutrons in a nucleus. Okay, and just bear with me. These densities, I just want to make sure everybody's on the same page. Point neutron density, point proton density. If you take the neutron density, fold it with the weak form factor of a neutron, then that gives you the weak charge density. Just like if you take the proton density, fold it with the electric form factor of the proton, you get the charge. Okay, and then there's a small term. The weak charge of a proton is small, so this is a small contribution. Let's see. Okay, great. And just to keep track of terminology, the RMS radius of the neutrons is Rn, the protons is Rp. The RMS radius of the weak charge density is the weak radius. Okay, and we'll talk about the neutron skin, which is Rn minus Rp, and the weak skin, which is the weak radius minus the charge. Okay, the weak skin is actually the observable point. You can't measure directly the point proton and neutron radii. Great. Okay, so this is a little cheat sheet to help with my talk. And then here's a model density. The point proton is the dashed red. You fold it with the charge form factor, the electric form factor of the proton, and you get the solid red, which is the model charge density. Just like the dashed black is the point neutron density. If you fold that with the weak form factor of the neutron, and then the distance from here down to there is the small weak charge of the proton. Okay, so the black line is what the experiments are about. That's the weak charge density of a heavy nucleus lead. This is from a simple relativistic mean field model. We'll get to the experimental density in just a sec. Okay, great. So the parity violating experiment basically uses all of Jefferson Lab. You have a polarized electron beam. It's accelerated to 1 GeV, and there are lots of beam monitors to control helicity correlated beam properties. Whenever you flip the spin of the beam, you want nothing else to change, and so you very carefully monitor position, energy, angle, and so on of the beam, and how those depend on the helicity. Electrons strike a target. It's a thick foil isotopically enriched in lead-208, and then two large 5-story high spectrometers integrate the scattered electrons. Great. So CREX 2 is a run for lead. The measured parity violating asymmetry, and we extract the weak radius of lead is 5.8 plus or minus 0.075 Fermi. So there's the weak radius. The charge radius is 5.5 Fermis, and a small correction for the form factors. The neutron skin, neutron radius minus the proton radius, 0.283 plus or minus 0.07 Fermis. So that's the CREX measurement of the neutron skin in lead. This error is the combined experimental error, which is dominated by statistics. The systematic error is much smaller than the statistics. Great. Want to extract the average baryon density in lead, and the procedure is to determine some average charge density and then the average weak charge density. This is basically the neutrons, that's the protons, and if we add these, combine them in the right way, we'll get the baryon density. Okay, so step one, the average interior charge density. We average by fitting this dotted curve. It's a Wood-Saxon. So we fit the Wood-Saxon to the experimental charge density with the wiggles. And then the normalization of the Wood-Saxon is the average charge density. Okay. So that's easy. Now we want to calculate or determine the average weak charge density. So in principle, we can do the following impossible two-step procedure. The first step is to map out the weak charge density as a function of R, measure parity violation of the whole range of Q squared, including the high Q squared, see all the shell structure, and then average over it by fitting the Wood-Saxon. Okay, we're just interested in the average interior density. Okay.
Chuck, beyond the fitting the Wood-Saxon, do you have a model independent or Wood-Saxon independent definition of what the average density in the interior is? Like integrating from 0 to 4 Fermi and taking an average, or you just think it of a
Yeah, so I actually do exactly that. I have a code which integrates from 0 to 4 and takes the average. But the concept nuclear saturation sets the average interior density. It doesn't tell you exactly what that is and exactly what interior is.
But I mean, you know, completely naively, I mean, the densities of the charge are weak, are not that interior.
Here's the experimental charge density. So the red line is actually pretty flat. And furthermore, I'm approximating, so my average is this dotted curve.
Okay, whatever assumptions we start with, put up with push out.
Oh, the value is a different question. So it's flat. It's certainly influenced by Coulomb.
Yeah.
And in fact, if you look really closely, and maybe this is what you're getting at, the density is low there, and this actually, the density is growing.
Okay.
And I think that's Coulomb.
Yeah, okay. And there will be some opposite trend in the weak or neutron. Yeah, okay.
So again, it would be wonderful to be able to measure the full weak charge density. And clearly the shortcut is to take a Wood-Saxon shape and fit that to experiment, and then use the Wood-Saxon. Okay. And so that's this curve here. This is the experimental error, and I'm going to talk about that in a second.
Those little oscillations are the little shells that are being filled. No.
Oh, this bump is the 3s,
Yes.
and that upward slope is Powell's Coulomb.
Okay, but there's also orbital dependence. But I mean, some are emphasized, right? Unless.
Okay, I mean, how this density comes about and is clearly non-trivial, and in fact, most density functional models over predict the shell life. Their bumps are too big. But right now we're trying to observe the average baryon density in the heavy nucleus. Okay, so we have this Wood-Saxon that we're fitting. There's a radius parameter C and the surface thickness parameter A. And then the normalization, which is what we're actually interested in. Okay. The area under this Wood-Saxon is the total weak charge of lead. The RMS radius, basically the radius parameter squared, and there's a little correction from the surface. Okay. And this is normalized to QE, and so actually it's nice with this form. You can analytically calculate this normalization, and here it is. Okay. So the procedure, basically the experimental input from PREX is the value of the weak radius, the 5.8 plus or minus 0.075. Okay. There's a little bit of a correction from the surface thickness that matters. So basically the density is the charge over the radius cubed. Okay. The weak charge we take from the standard model, but that's actually been measured accurately, not in lead, but in cesium. The atomic parity experiment at Boulder, Carl Weinman measured the total weak charge of cesium to 0.3%. Okay, so this guy is the standard model. This guy is from PREX2. We need a surface thickness. In principle, we could do a second parity experiment at a slightly higher momentum transfer and directly determine A from experiment. We haven't done that. So at this point, we take A from theory with a fairly generous error bar.
Sure. Another thing you could do is to grab one single point that use a base and prior on both R and A, and just, the two parameters stays one single experimental value with your priors, instead of having all the experimental information to R and all your prior to the surface thickness. That makes sense?
That makes sense. I'm not sure. It helps explain what you're doing to use the linear combination.
I don't know you did.
Okay.
So you put an error of 2.6%. The experimental error on.
Yeah, so the experimental error is simple to understand. It's dominated by R weak. The density is Q over R weak Q. So PREX measures the radius to 1.3. If you square that, you get about 4%.
The error in the precipitate definition. How well is this broken zero defined that you assume that it's
So
the word could some cutoff over which you average? I mean, the sharp gradient.
So let me just say, I'm defining the averages of this Wood-Saxon procedure.
Okay.
And that's the measurement. That's what I determined. And of course, you're free to choose something else.
So essentially, there's no model error. So the fact that there's an assumption about the shape, the assumption about the diffuseness, is this right?
So
The number does not include the model error?
So, let's see. This shading here is mostly R weak. There's some contribution from the uncertainty in A, the surface. Okay, the surface doesn't contribute very much, so that error bar is relatively small. just because A is so much smaller than C.
In R.
So.
Because it's cavity both, so it's because it's serial cavity with charge of proton, and then it causes cavity in overall baryon density.
So let's come back to Coulomb.
Okay.
But we're not there yet. We're almost. Okay. So the claim is there's a 4% error here. That's dominated by PREX and R weak. That includes some estimate of the theory uncertainty for A. You can make it bigger if you choose. I would really love to measure it. That would be better defined. Okay, so this is 4%. Basically, we're adding this and that, and the uncertainty in the charge is small. So when you add something with a very small uncertainty to the 4%, what's left over, this error, basically this size is the same as there, but now it's only 2.6 or 2.8%. Okay. So that, whoops, let me see, where am I? Great. So the average interior baryon density in lead is 0.148 plus or minus 0.0038 Fermis. This error is 2.6%. And so with my definition of the average, this is a measurement of the interior baryonness.
So how was the rodeo apartment of 116 come from?
That comes from one of BTEC's density functionals. And I think the best argument for that, and let me come back to that question just a second. I have to get to Coulomb first.
I can comment. When I was a student, it was 0.17.
Uh-huh.
And this is 1.5 digit accuracy.
Inflation.
So the deflation. That's right. I think you're right, pal. The older we are, the bigger it was.
Of course, that 0.16 will be for infinite matter.
So that's the interesting.
0.17 was also for infinite matter. And just that there are two digits given. The first one is bad. It's a really nebulous.
So
Sorry.
okay, this is we're exactly at this point now. This is what we measure. So this is lead. This is a theoretical calculation in infinite nuclear matter. So Christian Dischler et al. At N3LO, they did a chiral effective field theory calculation, infinite nuclear matter. And they get the red line and the Sarah bar, and they work pretty hard to estimate the error in the saturation point, and they have this band. Okay, so that's the chiral effective field theory calculation of infinite nuclear matter, and it saturates from something like 0.14 up to 0.20. So this is 0.14 and that's 0.20. So this is a calculation of the saturation density of infinite nuclear matter in N3LO chiral. So that's a theoretical prediction. Okay. This.
Why do you choose to use the blue one and the red? The red is small, is narrow.
Oh, actually, the red is N3LO, the blue is N2O.
Yeah. So isn't N3LO then?
Yeah, so I did actually use the red here.
Oh.
This is the red, the blue would be. Okay, and then the interesting part that Al's constantly badgering me, I can use that. How is the finite nucleus density related to infinite nuclear matter? Okay, there's basically three effects that are all thought to be small. One is Coulomb. So you've arbitrarily and artificially turned off Coulomb for the nuclear matter. When you turn it on, it's pushing the protons and the nucleons out in lead. So Coulomb lowers the interior variance. But then lead has a surface, and surface tension pulls in. So surface tension raises the baryon density in lead a little bit. So there tends to be some cancellation between Coulomb and surface. Another small correction is the neutron to proton ratio.
So if I look on water droplets, the inch where you don't have Coulomb, the interior density of the very middle of the water droplet is higher than it would be in bulk water.
By a little bit, and water is pretty incompressible.
Okay.
But I think certainly more incompressible with surface tension.
Yeah.
That makes sense, because otherwise you will increase it and you have more surface. So you.
Oh, yeah.
Okay, and the third correction is the neutron to proton ratio. Tradition says we should plot the saturation density of symmetric nuclear matter, so equal numbers of neutrons and protons. While that, of course, is neutron rich. So maybe we should consider nuclear matter with the same ratio of neutrons to protons as lead 208, and ask where that's at. So you could make a small correction. The difference in the saturation density of slightly neutron-rich asymmetric matter compared to symmetric. The asymmetric matter will saturate it at slightly lower density. And that depends on the symmetry energy, of course. Okay, good. Then I may have gotten through American. Great. So that's experimental observation of the interior baryon density of lead, and I think that's a really fundamental quantity. And I go so far as to say I'm proud of this measurement, especially because I didn't have to do all the work to do the parity violation. Great. What causes nuclear saturation? Why does nuclear matter saturate at this density? If you have water molecules, the answer why is 1 gram per cubic centimeter, 1 gram per cubic centimeter. And it's pretty easy. The size of a water molecule. You pack them in, and that gives you 1 gram per cubic centimeter. I mean, there's a slight subtlety. Why is ice a little bit less dense than water? But basically, it's just the size of the water molecules. Okay. That doesn't work for nuclear matter. The size of the nucleon cores, where the phase shifts return repulsive, we have some hard cores, but those hard cores are only like half the Fermi in size. So the hard cores are too small to explain saturation density. And indeed, Ben-Day had nuclear matter saturating at twice the correct density. So there's this complicated interplay where you have the tensor 2 nucleon force, you have repulsive 3 nucleon forces, etc. And somehow these all magically cause nuclear matter to saturate with the. Okay. Perhaps these cores are still there, they're just hidden. Perhaps there is a higher density where the cores touch and nuclear matter turns very repulsive.
There's a question from online.
Sure.
On Joe, like low density matter clusters
Does this play any role in the analysis of Newton's theory? Although there's no.
Oh, we'll get to the skin, in a little bit. We're measuring, an RMS radius of a charge distribution. If you have complicated correlations in there, 2-body or 4-body correlations that make alpha particles, we're measuring the 1-body density, and that has a radius. If you want to describe it with clusters, you may. We haven't probed experimentally the clusters yet. We're only measuring the 1-body. So I guess the short answer is it could. Okay. Great. So let's think of the skin now. So we've focused on the interior density. The pressure of neutron-rich matter pushing neutrons out against surface tension, and a high pressure gives you a thick neutron skin. And it's the same pressure that's holding up a neutron star. A high pressure gives you a big radius. This guy is 18 orders of magnitude larger. Same pressure, same neutrons, same strong interaction, same equation of state. Great. So let's compare measurements in nuclei with astronomical observations of neutron stars. We can measure radii, so the PREX and the CREX experiment, I hope to get to, measuring neutron radii of nuclei. NICER is an X-ray telescope that measures the radius of neutron stars. And then the other class of measurements is polarizability. If you scatter one nucleus off of another nucleus at large distances, you can Coulomb excite one nucleus and use Coulomb excitation to measure the electric dipole polarizability of a nucleus. Okay, so I'll get to that in a little bit. Alternatively, you can scatter 2 neutron stars and let the gravity from one neutron star tidally excite the other. And that allows you to measure the mass quadrupole polarizability and the gravitational wave community don't know any better. So they don't call it the polarizability, they call it the gravitational deformability. And what is the deformability? That's the quadrupole polarized. Okay. So NICER, this X-ray telescope, measures the neutron star radius from an X-ray light curve. And there are some systematic errors associated with the modeling of that light curve. If you're measuring the dipole polarizability, it's an electromagnetic observable. So in principle, you can do the experiment pretty cleanly. There's some issues with how high and up you go to measure all the strength and how you separate the dipole from other multipoles, so on. But never mind that. Just want to keep track that to interpret the dipole polarizability, you have to sum over a range of excited states. And so it would be great to have more ab initio calculations of the polarizability of this sum over excited state. Okay. LIGO measures the gravitational deformability. The present measurement is statistics limited. And the systematic errors can be well controlled, and that's important. We'll get to that. if I get there. Okay. And I talked about a dipole polarizability. Start in the ground state, have a dipole operator, say the electric field of the photon, take you to a deformed excited state, square that, going like the size of the system squared, divide by an energy denominator, sum over all the final states. If it's a Coulomb system like an atom, the energy denominator goes like 1 over r. So the dipole polarizability scales with the size of the system like r cubed. Great. Do the same thing with the mass quadrupole. So you start with a round neutron star, go to an excited state of a neutron star that's deformed. This scales like the radius of the star squared. You square it, so the numerator is r to the 4th. The energy denominator for a gravitational system also scales like 1 over the size. And so this deformability scales like the size of the neutron star to the 5th power. Okay. And LIGO, by observing this neutron star merger, has set limits on deformability, and I'll show you those. Okay, so very quickly, we've got the radius of a 1.4 solar mass neutron star, the deformability of a 1.4 solar mass neutron star. This is dimensionless. And here's the LIGO upper bound. So deformability smaller than something like 600 are consistent with LIGO. The blue dots are one particular relativistic energy functional with some parameters describing the symmetry energy. And if you change those parameters, you can move along this curve. You get bigger stars when the symmetry energy rises faster. And this blue curve is something like r to the 5th. So you get bigger stars and bigger deformability. And
So you don't talk about a lot number, but the relationship to the r to the 6th.
this curve might be r to the 5.5 or something. 5 and 6 is close enough as far as my limited abilities. Good.
Can I ask a question?
Sure.
What do you mean, what kind of upper limit are you talking about?
Yeah, so it's something like, I think, 90%. Yeah, and that's a fair question because the PREX limit is 1 sigma. So okay. Nicer measures neutron star radii by looking how the curvature of space fills in the minimum in an X-ray light curve. If you have a hot spot in the front, you see it, but if you have a hot spot in the back, you only see part of it, and the part you see is how the curvature of space bends light around. And the smaller the star, the more space is curved around it. So a small star has a filled-in minimum to the X-ray light curve as a function of rotational phase. Okay, and here is one of Neisser's observations on this particular pulsar. The radius is 13 plus or minus about 1 kilometer. So that's an example of an X-ray observation. And now with this blue functional, we can also use it to predict the neutron spin in lead. So I've written a third axis up there. And here's the PREX measurement of the skin. It predicts a somewhat big pressure, but if you extrapolate from nuclear densities up to about twice nuclear density in the neutron star with this density functional, then these skins suggest 13-kilometer or larger neutron stars. So relatively thick skin in lead suggests the pressures. Okay. So PREX is certainly consistent with nicer. It's in slight tension. The LIGO suggests that neutron stars are smaller than about 13, and PREX suggests that they're bigger than about 13. So they are weak tension, but not inconsistent at something like the 90%.
How do you define the size of something with a diffuse surface sitting on?
The diffuse surface of a neutron star is about yay. The neutron star atmosphere is very short, and the gravity is so strong that the gas basically just collapses.
But still, the density changes as you go inside, so.
Yes. So a cold neutron star has like a new.
So the radius is well defined,
That's right.
even if the average density or whatever requires to be very careful about it.
Yeah.
For the rest of the.
Okay. Let me just Reed Essek, Ingo Tooth, Achim Schwenk, and coworkers used a flexible equation of state, where basically the pressure at different densities is not particularly correlated, and they also used a correlation. L is the density dependence of the symmetry energy. It's essentially the pressure of neutron matter at nuclear density. A correlation between L and the skin thickness of lead. So if you believe that correlation, then looking at astronomical data, which is basically nicer and LIGO, observing neutron stars, then they got this curve here for the skin thickness in lead. So the PREX measurement is here, including the PREX measurement is consistent with the astronomical observations, and you have a pretty broad distribution of skins. You could also have thinner skins than lead saw, being consistent with astronomical data. So basically you can have a variety of pressures at nuclear density and still fit the astronomical data. What they then added is chiral effective field theory calculations of the pressure of neutron matter up to nuclear density. Okay? And they claim that these chiral calculations basically could calculate L, and the error bar in L was pretty small. So if you use this correlation, they could predict the neutron skin in lead 0.17 plus or minus 0.04. So chiral effective field theory is now making predictions for L and therefore predictions for the neutron skin. Okay. This skin is smaller than PREX, but you have a relatively big statistical error there. So these are consistent at 90%. And basically, this is what you want to do. We want to test chiral effective field theory calculations of neutron skins. We want to test it as sharply as possible. Want to make the sharpest comparison with parity violating measurements of neutron skins. Okay. And first of all, this isn't really, they didn't really calculate lag. They used this correlation with L. So you would like it where the chiral effective field theory actually is calculating what you observe. And you want to use an observation with this small n. Okay. And that was the motivation to test chiral effective field theory as well as we can. So we have the second parity violating measurement on calcium-40. Okay. And actually, we can go right down there. We need a stable nucleus for a target. We'd like it to be neutron rich to measure the neutron scan. And doubly closed shell actually turns out to help a lot. So the only stable neutron rich doubly closed shell nuclei in the world are calcium-48 and light-2. So those are special. PREX is a measurement on lead. Lead is bigger, it's maybe better for inferring the pressure of neutron matter and structure of neutron stars. The CREX, the measurement on calcium-48, the smaller system allows more direct comparison to microscopic chiral effective field theory calculations in the finite nucleus calcium-48. And the scan is very sensitive to 3 neutron forces. So they're predicted by chiral effective field theory. They're difficult to directly observe in few nucleon scattering. And that's one of the things you're testing. Okay, great. So CREX, the large collaboration worked really hard on controlling systematic errors. 2 GeV electrons scattering about 0.87 inverse Fermis from calcium-48. For time, let me just emphasize they worked really hard and gave a lot of thought and care to controlling those systematic errors. Okay, and from the measured parity violating asymmetry, you can extract a weak form factor, the Fourier transform of the weak charge density. And one nice way to consider it is the charge form factor, the Fourier transform of the known charge density. And then this is the PREX measurement there. CREX measurement. So this is experiment. So this is what we observed. That combination 0.0277. And this error is experiment. Okay, and there's no model dependence here. Where this is basically can be directly deduced from the measured parity violating asymmetry. Okay, and given time, let me just plot this. So here's the charge minus weak form factor in calcium at 0.87 inverse Fermi momentum transfer. This is the experimental point. For lead, it's the same quantity. PREX is the 0.4 inverse Fermi's momentum transfer. And this quantity scale grows with the neutron scan. So a big Rn minus Rp is up here. A small scan is down there. Likewise, a big scan in lead is out here. Okay. And here's the joint 1 sigma and 90% confidence level contours for the 2 experiments. The black circles are a series of relativistic density functionals from very small L, actually L less than 0 down here, to very big L over 100 up there. So this is a tremendous range of symmetry energy going from very small skin to very big skin. And here are a series of non-relativistic density functionals. Unit F1, for example, slightly underestimates the skin predicted by PREX and lead, and slightly overestimates the skin in CREX, but it's a pretty good compromise. So most models tend to overpredict CREX, so the CREX experimental skin looks small, and underpredict the skin in lead. So lead, compared to most models, seems to have a big skin. Okay. And these are our experimental results and our central values and error bars, and we're sticking to those. Okay. From the form factor, we can extract an Rn minus Rp, but this is model dependent. There's no unique way to get the radius out. So there's a model error in doing this. There's no model error here. There is a model error that's pretty big, and that's the width of this band here. And that's different shapes, weak densities have the same form factor, but give different weak radii and neutron radii. So CREX is run at too high a momentum transfer to uniquely get the radius. Okay, so the radius has a model error. The form factor does not. So if you could, please compare your beautiful theory to our beautiful measurement of the form factor and not the radius. Okay, great. The model error in PREX is very small. So you can use neutron radius and lead, no problem. Great. Parity violating electron scattering is free from most strong interaction uncertainties. We've accurately included Coulomb distortions. We know the charge density. We know how to do that. Experimental system errors are small. The model error from the shape and CREX is completely avoidable if you just use the form factor. Great, and let me emphasize all the people, not me, who did the hard experimental work and actually did the measurement. And also, my student, Brendan Reed, was vital, did a lot of work in helping with the analysis. So thank you very much. Appreciate your patience and your questions. So thanks very much.
From local audience here. Yep,
Thanks for the minutes. I was wondering whether in the future any of this can be done at the PRC or not. Very well.
So the next step is actually MESA is a small electron accelerator in mines. People are thinking about parity violating at the ERC. And so the short answer is I'm not sure if people are thinking.
And to keep in mind, at that scale, the weak boson and photon have the same Hawking string.
Yeah, I mean, at high Q squared, the parity violation is bigger, so that makes things easier.
Very small scattering. Q squared is one.
And that's what you're trying to observe with the parity. The testing the standard model or the structure of nuclei is hard because the moment transfer. I don't know if you can get around that.
Do we have questions from online audience? Okay, it's done, that's just, okay.
If you were to speculate with the extrapolation of the density that led to
Mhm.
infinite neutron matter. From this point, I think it was point 45
Oh.
or something. What do we get instead of 116?
Yeah. You're close. It depends on how you do the extrapolation. Let's see,
Right.
there we go. So the naive estimate is let the Coulomb and the surface cancel. And then the prediction, so the zeroth order prediction is nuclear density is 0.15. We wrote a paper and we talked about the extrapolation. And then I realized that it's dangerous and confusing for the experimental measurement to talk about how we extrapolate the nuclear matter. The theorists should just try to predict the finite nucleus quantity. So I try not to say any extrapolating.
Couldn't you just make a calculation where you vary the parameters of your model and make a correlation plot between what you define as interior average density, and you can define it any way you want, and that saturation density at infinite nuclear matter, and see, the correlation is 1, we're good, or you need to add an extra 0.1 to get from one to the other.
Yeah, that's exactly what we did in this 2020 or 2021 paper. If there are ambiguities in that extrapolation, it could confuse the issue. So we measured as cleanly as we could the interior baryon density of lead, and now theorists working chiral effective interactions to try to predict.
What is the value for calcium?
Oh, the interior density in calcium, we didn't do it. Wood-Saxon is a pretty bad fit. There's a big bump in the middle of calcium. So the interior density of calcium is much higher. Let's see there. So I think that's actually calcium 40, but calcium 48, the charge density is similar. Calcium looks much denser than lead.
So assuming that interior density of a neutron star is say, what, 4 times nuclear density, and the speed of sound obviously changes a lot between saturation density and 4. And so when you get a number, an estimate from one of these stellar measurements, it's just one number, which might be changed by a factor of 5 to that radius of the neutron star. Which densities do you think it's mainly sensitive to? The outer part of the neutron star, the middle, or some?
The radius and the deformability are sensitive most around twice nuclear density. Yeah. The maximum mass of a neutron star is a high density, so that cares about higher densities.
Okay, if you don't have more questions, thank you.
Right.
So Chuck, I said oxygen